All right, we should be recording. This should be on. Everything should be good now. 6 seconds in. Right, guys, welcome back to the Isaac Devs Corner. So today we're going to be covering the TCP IP protocols and architecture. So today's agenda is pretty simple in a sense, but there's a lot of content to get through. So this is a continuation of the networking series I've been doing. It's all in the playlist if you want to start from the beginning. But without further ado, let's get straight into it. Okay? First thing. Outline. So we're going to be discussing the TCP/IP architecture model and the transport layer. We're going to be discussing transmission control protocols, TCP, very common one. You got the user datagram protocol, which is the UDP, IRP, which is address resolution protocol, and internet control message protocol, ICMP. Okay, so as you can see here, I've just made a little quick diagram here that's got the applications on where they are. So you got the TCP and UDP in the transport layer. You've got your IP on your network, etc., etc. Now, TCP/IP architecture, model, and transport layer. So the network architecture models, the open source system interconnection, OSI interface model, that's sort of like the model that it all runs off, and the transmission control protocol internet IT TCP/IP suite model, which is the more essential, more refined version of the OSI. Okay, so the TCP/IP model has 4 layers and was created in the 1970s. The model describes general guidance for designs and implementations of specific networking protocols for intercommunications. TCP/IP specifies how data should be formatted, addressed, transmitted, routed, and received at the destination for end-to-end connectivity. So you can see OSI is the more hefty version, and TCP/IP is the more refined version of that model. So there's another demonstration there. But the core protocols in the TCP/IP suite are the TCP and the IP. Okay, so you talk about transmitting and how data interacts. Operate in transport and network layers of the OSI model, provides basic services in protocols on these layers. So you can see the protocols there on the different, you got the TCP and you got the OSI, so you can see how they sort of interact. Basically, TCP has confined everything of the application presentation session into that same one, and vice versa with network, you've got data link and physical in that network access layer. So the role of the transport layer is responsible for end-to-end communications, reliability, interface between applications and lower layers. Transport layer includes 2 protocols. So as we just looked in the diagram before, it's got the TCP, it's got the UDP. So the TCP is a connection-oriented protocol and is designed for reliable transfer of information. So this is things like maybe you're loading a web page and you need everything to be set up. So you need it to be connected and you need a reliable connection. Right? So UDP is user datagram protocol. It's a connectionless protocol, so you don't have to establish any sort of security, not security, but a handshake per se. We'll get into what that means later because it's complex, but we'll get into that. But basically, it's more free flowing. The data doesn't have to be sent and approved, and it's none of that. It's just you have a connection and a data just sent. So connectionless protocol, and it's designed for efficient communication, generally of small amounts of data. So they're very different, but they both send data in a way. Okay. So working with segments and datagrams. So transport layers work with units of data called segments. So TCP or datagrams, UDP. So they have different names: segments, datagrams. Both TCP and UDP add a header to the payload. The transport layer then passes the segment to the internetwork protocol, IP. With incoming data, the transport layer receives the segment from the internetwork protocol, processes it, decapsulates it, and sends the resulting data up to the application layer. Okay? So you're receiving the data, you're processing it, it's going through the IP Internet Protocol, then it's being pushed up that OSI/TCP/IP model into your application for you to then view it. Identifying source and destination processes applications. So a port number is a way to identify a specific process application to which an internet or other network message is to be forwarded when it arrives to a server. So for TCP and UDP, a port number is a 16-bit integer that is put in the header appended to the message unit. TCP and UDP use port numbers to specify the source and destination application layer protocols. So detect data integrity with a checksum mechanism. To protect data integrity, TCP and UDP provide a checksum like a cyclic redundancy check, CRC. We've gone over this before, which is error detecting code. In the previous videos, we went over this, so you can check them out. Intermediate nodes don't recalculate the checksum in the transfer layer. So if your data corruption occurs during the transmission, the final receiving host detects the checksum, error, and then discards the data. So it's not going to be checked in the intermediate nodes. It gets checked on the final receiving node. And if it's wrong, then it will get dumped. And yeah. Process to process communications. IP is a host to host communications. So transport layer protocols such as TCP and UDP are for delivery of messages to the appropriate application program, i.e., process to process communications. A computer may be running several programs at the same time. To make every connection unique, we need to use the IP address and the port number to establish a unique identifier on the machine. So to define a socket and endpoint or socket address. So you need to make sure you have different connections for each application and program that you're running, because you can have dual things running at the same time, but that's all done via these protocols. So the socket address unique connection. Every connection has two sockets or endpoints. So source IP there, you've got that, and you've got a socket in the end, 2525, and destination port is 80 on that example. So this connection creates a unique virtual channel which you shall communicate from. So the use of ports allows devices to run multiple servers and applications. So you've got, for example, in that top bit here, over here, you can see we've got the client talks to the web server, and the web server is talking via 80, and you're on 6,000. The client is talking via email, you're on 8,000. This one's on 25. So you're creating a socket. So you have the IP address plus the port number, which is going to be this and this and this and this. So this will create a socket. An IP address alone is not sufficient for running an application, as the host can run multiple applications and all services. Port numbers. Port numbers range from 0 to 65,535. Three types. We have well-known ports that range from 0 to 1,023, operating system or administration use. We have registered ports, so 1,024 to 49,151. Network users process with no special privileges. Dynamic and or private ports. So this ranges from 49,152 all the way to 65,535. So normally for clientele use, no restrictions on these. Okay. Now port numbers here, we have a few with protocols assigned to them. We've got different sort of things like the FTP. You got the SSH, which is the secure shell, the Telnet, the simple mail transfer protocol, SMTP. Sorry. You got the HTTP. You got HTTPS, you got TFTP, different types of protocols, as you can see the names of there too. And it tells you what protocol they're using. Some of them use dual, they use TCP and UDP. Some of them use just TCP, some of them use just UDP there, okay? So we'll get into TCP transmission control protocol right now. So TCP features, so error control. To transmit lost segments, TCP uses retransmission timeout, so RTO. When TCP sends a segment, timer starts and stops when the acknowledgement is received. Checksum to detect errors. Okay? Now flow control. Flow control ensures the destination does not become overwhelmed. Only a certain amount of data can be sent at one time, controlled by a sliding window mechanism. Now, I'm not too sure how exactly those things work, but you can sort of envision the logic behind the main premise. Now, retry mechanism can retransmit if no acknowledgement has been received. So the TCP is a connection-oriented protocol. So before data transmits, there's a three-way handshake, and I was just talking before, this is the handshake thing, we'll get into it, but you need to establish a connection to make it part of this connection-oriented protocol. So the process with the destination, then it's data transferred, so you need to establish the handshake first. And then after the data is transmitted, the connection is terminated by a four-way handshake process. So it's like you're going to handshake someone, do a deal, and then once you finish the deal, you handshake and you leave, kind of thing. You can envision it like a logical format like that. But yeah, TCP offers a full duplex service. Data can be carried in both directions at the same time. So the TCP header, you got source port address, which is 16 bits, destination port address, sequence numbers, acknowledgement numbers. So the sequence numbers and acknowledgement numbers, they're used to sort of identify and check for the handshake. We'll get into that in a second. You've got your data offsets, you've got your checksum, you've got your urgent pointers, and some stuff I don't really truly understand here, like options and padding and that. So, but that's definitely something you can research. Um, yeah. So basically, this just talks about the different examples here. So your source port. So we go back here, source port, destination port. Here you got your sequence number, and you got your acknowledgement number. So the acknowledgement number is a 30-bit field, which is down on this one here, which indicates explicitly that the specific set of data received successfully, indicates the next byte expected, sequence number from the other side of communication. And also the sequence number down here, up there, sorry, defines the first byte of this datagram. The numbering does not necessarily start from 0. So TCP/IP header field, we've got the 9-bit control bits. A set of 6 standard and 3 extended control flags indicates the purpose and controls of the segment. So, yeah. Anyway, so URG, these are just things we need to know. So URG informs that the recipient that a certain data within the segment is urgent and should be prioritized. The recipient evaluates the urgent pointer. The acknowledgement, this is the ACK in the FINAC sort of schematic or thing, indicates that the device sending the segment for an acknowledgement. So it indicates that the device sending specific. You get the PASH, so request a push to send immediately. These are the ones that I'm not really seeing personally. Resets the connection. And you got the sign. So yeah, in this one you got the indicates that the segment is being used to initialize a connection, and you got the indicates no more data from the sender. So your ACK, sign, and FIN. You've got your 16-bit window that indicates the TCP receiver, buffer and bytes, checksum, urgent pointer. We went over that. The 3 stages of the TCP connection. So connection establishment with a 3-way handshake, data transfer, connection terminated. So as I said, imagine you're going to meet someone, give them a handshake, do a deal, handshake done, your deal's done, and you walk away. So the connection with 3-way handshake, because TCP is a connection-oriented protocol, it needs to first initialize a virtual connection. So it's done through the 3-way handshake and synchronize the connection. This connection remains open for the duration of the interaction between the two ends. So, for example, client A sends a TCP synchronization, a signed segment to the destination device B, usually a server of some sort. Now, the destination port is specified and the source port is assigned dynamically. Use 3 segments establish a TCP connection. Segment 1, A, issues a message to B for initialization. B sends a message to A for initialization acknowledgement. And 3, sends an acknowledgement back to A, sends one back to B. So the 3-way handshake is a fundamental process in the community networking that establishes a reliable connection between 2 devices, typically a client and a server. It's often used in the transmission control protocol, TCP, a key component in the internet that ensures reliable data transmission. So here's how it works in 3 steps. So basically you have your sign, which is your client initiation. So SYN for short. So the client starts the process by sending a packet with the SYN flag set. And that was in the section where you can put that in. This is like saying, hey, I want to talk to you. Let's get ready. So that's basically what's happening. And number 2 is a server acknowledgement and synchronizes. So SYN ACK. So the server receives the client's request and replies with a packet with both the SYN and ACK flag set. This means I recognize you, I'm ready to talk, and here's my information for the communication. That's your acknowledgement. Now the client also sends a ACK back. So finally, the client sends an ACK packet to the acknowledge the server's information and confirmation of the connection. Both devices have synchronized their communication parameters and are ready to exchange data reliably. So in visualization, it looks like this. Your client sending your signed segment, your server's sending a response, SYN ACK, and then you're sending a acknowledgement back. So SYN ACK ACK is, I guess you could say it like that. You got your sequence number, it's amplified by 1, and yeah, so that's that. You've got your acknowledgement and etc. So as time goes on, you are doing it like in a chronological, so boom, boom, boom. And you've basically worked out like that. So in terms of the sequence number, we'll just go back. We can check out sequence and acknowledgement again. So if you go back here, the sequence number defines the first byte of the datagram. So that's like data stuff. It tells you like the storage, how much it is. The numbering does not necessarily start from 0, and the acknowledgement indicates specifically that a specific set of data received successfully indicates the next byte expected in the sequence number on the other side of the communication. Okay, so we're going to go to the next one. So the connection termination. So the one before we just did was the connection. This is the termination once your data has been sent and you want to, leave the communication. So a fin from the client server. So the client initiates the termination by sending a packet with the fin flag, which means finish. This signal is in its intention to close the connection. The acknowledgement from the server to client. So the server acknowledges the client's fin request by sending back an acknowledgement packet back. This indicates that it has received the fin and is prepared for the connection to close. Fin from server to client. This server now sends its own fin packet to the client, signaling that it's also ready to close its side of the connection. So fin ack fin. So now the server is ready to close. Now the acknowledgement from the client to server. The client acknowledges the server's fin by sending a final ack packet. This confirms that both parties have successfully agreed to terminate the connection. Key points. Each step involves a single TCP segment with a specific flag, fin, or ACK. The process ensures a graceful and orderly termination of the connection. It's a fundamental part of TCP's reliable data transmission mechanism. So in visualization, it looks like this. So your client wants to end the communication, so you have a fin. It receives and sends an ACK, so it tells the app to close, receives the acknowledgement, waits for the fin server, and the app is ready to close, so it sends another fin, receives the fin, sends acknowledgement, and then you're ready to close both. So wait for double maximum length segment, so LMSM there. So, and then you can, your connection's terminated. So the UDP user datagram protocol. Connectionless transport protocol, a data delivery service is unreliable. So this is not a reliable service. It's more so just for like gaming and sending things that don't even be specific. Not that they don't even be specific, but they can be lost and things are not as reliable as TCP. Well, TCP is reliable, but this doesn't have that reliability in that same sense. So useful situations, great volume of data transferred quickly. This uses a different sort of. It's not a FINAC or ACK sign setup. It's more just sending and responding. So the user datagram protocol. This is what the header looks like. You have a different sort of setup here. It's much more simple. So there's not much to it. Source port, destination port, length, checksum, payload. So each UDP is called a user datagram, has a flexible header of 8 bytes. You got the source destination, which is 16 bits. You have the port numbers between, etc. We went over that. Checksum is optional for IPv4. So it's a no connection handling. Each datagram is independent message that the sender transmits without UDP providing any way to establish, manage, or close a connection. So there's no delivery guarantees. Datagrams are not sequenced and not acknowledged. Datagrams are sent without any prompts of delivery. Application layer must provide tracking and retransmission mechanisms. No error checking, no guarantee that the packet is fully received. So this is much less vigorous in checking things. So it's more just blasé in a way it runs. So applications, UDP is used while error checking and correction is performed by the applications such as DNS, DHCP, TFTP, IPTV, RIP, all these different types of protocols here. The address resolution protocol is is used to resolve a logical IP address to a physical MAC. We've now moved topics, by the way. Well, not topics. We've now moved to the address resolution opposed to we were just at the UDP. So this is about protocols. So this one is responsible for logical to physical addresses for a local area network communication. Operates at both layer 2 and 3 of the OSI model. Every frame contains both a MAC and a IP, source and destination address. When a packet is ready to be sent to a network access layer, the destination's device MAC address must be retrieved before the frame header can be constructed. The source device needs to obtain the MAC address of the destination device to deliver data. So it needs to know the MAC address. It needs to know the source device needs to obtain the MAC address of the device sending to deliver data. Yeah, cool. So an ARP is a reply request pair of transmission on a local network. So it's a request reply. The originator transmits a broadcast request hardware address to the target host. The target host then replies a unicast back to the originator with the hardware address of the target host, aka the MAC address, which is assigned to every computer or device. When an originator on the IP-based network has an IP datagram to send to the target host, it will first check if the target host MAC address is in the ARP cache or not. Then starts the required address resolution process. If the target host is not in the same network, then it will send a broadcast ARP request to the network and then wait for the ARP reply. If the target host is not located on the same network, it will send the datagram to one of the default gateway routers. We won't have the default gateway. It sort of gets it out on the network for forwarding. So yeah. Cache. To avoid sending an ARP request every time an IP packet is sent, devices still learn the mapping of the IP MAC address in the ARP cache, temporary location on the RAM. So RAM is your sort of memory that is malleable. It's easy to access and has a really much faster than the stored hardware on your normal storage. So this is readily and accessible at any really quick for RAM. So ARP cache entries are not kept indefinitely. Most devices keep an ARP entry for only a few minutes after it is last used to avoid storing outdated information. So, which could result from a changed NIC, which is a network interface card or IP address. An ARP request is sent as a broadcast message so that every host on the network records the mapping of the requester's IP and MAC address to its ARP cache table for future reference. So the frame format. A Mac hardware address is a 48-bit long, expresses 12-bit hexadecimal digits. We've gone over this before in the previous lectures, I believe. The first 6 hexadecimal digits assigned by IEEE to identify manufacturer or vendor. The organizational unique identifier, or UI. The remaining 6 hexadecimals are assigned by the specific vendor interface. Serial number, blah, 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 is used as a broadcast MAC address. So, yeah. We've gone over MAC addresses before. I think it was in one of the videos about networking or something. I've kind of forgotten actually. I don't know, one of them, but it's in that playlist we've gone over. But yeah, so it's a request reply system. So ARP is a two-step process within a network when a host originator A begins a conversation with a target host B. A is aware of B's IP address, but does not have B's MAC address. A is unable to send a unicast frame to B. So A sends a ARP broadcast frame to B, request B's MAC address. Since it has the broadcast or host on the network, receives the ARP request. All hosts scan the content of the ARP request to determine if they are the intended target. The hosts which are not the intended target discard the broadcast frame. So it looks like this. So B is a target of A ARP's request. It sends a ARP reply back to A. Since B knows who sent the initial ARP request, it sends a ARP response unicast directly back to A. So you can see this happens here. Blah, blah, blah. Who is this? Tell blah, 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 blah is at this MAC address. So yeah, that makes sense. All done on the ARP protocol right here, as you can see. So yeah, as you can see here, you have a request and a reply. So it's got the request and reply here. This is actually, this application they're using is like a software that lets you check. I think it's called Packet Tracer or Wireshark. Wireshark, no, it's Wireshark, yeah. Yeah, so this gives you information to see what's going on, who's the sender, who's the target, and etc. So RP, so let's say direct delivery to A to B. A sends out a broadcast ARP request message to B, C, and D because you're on the same network connected via a switch. And they all receive this broadcast address, but only B responds because it knows it's the target when it looks at the MAC address when it receives the everything. So responds with a unique ARP message back. Indirect delivery, A to C. So you have A, and then you have a switch, and maybe a router's there and a switch there. So A sends out a broadcast ARP request to a message, the router's MAC address. The router responds with an ARP reply, unicast. The router upholds the received data and then processes the relay. The router sends out a broadcast ARP request to the request for C's MAC address. C responds with an ARP via unicast. The router repackages the data layer 3, layer 2, and then forwards it to frame C. So yeah, it's a more complex process when you've spread out like that. So resolving the MAC address from the IPv4 address. So ARP message, ARP broadcast, ARP reply. So yeah, you can see. So a broadcast message, what is your MAC address? So 10.0, sorry, .0.0.5. Not me, not me, not me. It must be the monkey, right? Yeah. aka a unicast message reply, my MAC address is etc. So it's kind of asking everyone, and then the person who has that response basically is what's occurring. And then we'll go all the way down to old mate there. And yeah. So when communications go wrong, ICP-MP, we have moved on. So the destination, an ICP is Internet Control Message Protocol. The destination host is unreachable. This is when the IP address is wrong or the host does not exist. The destination port is unknown. There's no particular application that matches the TCP port number. The destination network is unknown. The IP address is wrong. We've already went over that. Datagram on the network is too long. Time to exceed value expires. Congestion occurs at intermediate routers. So this is like the error stuff. So the ICP reports errors but does not correct errors. ICP always reports back to the originator. Generally, IP does not track of which routers have been. Error correction is left to high-level protocols. So value of protocol field is 1 for ICP messages. So there you go, right there. ICP-MP messages include 8 bytes data area of problem data gram to allow originator to identify the cause of the problem. ICP-MP is a network layer protocol companion to the IP. ICP messages are encapsulated inside the IP datagrams before going down to the data link layer. So as you can see here, this is all done. Let this little cool animation play. It's very slow. Just, yep. Man, that is very slow. So your IP header, and then you have your ICP-MP plus data equals IP data. Yep, and you get your frame data and your frame header trailer. So types of ICP-MP. So you have your querying, you have your error reporting. So querying is the echo and time stamping, and your error reporting is like destination unreachable, time exceeded, which are pretty common ones that you experience. So ICP assists the diagnosis of some network problems. Sorry, it often occurs in pairs. Queries and replies assist in obtaining specific information from routers and hosts. It is used by routers and hosts. So performs error reporting via and reply and querying for the internet protocol. Returns error messages back to the originator. Reports errors, invalid IP address, invalid port numbers. Time to live equals 0 of a packet. You can run application. You got ping and you got tracer. So yeah. Destination unreachable. Let's quickly go over that one. That is one where the TTL would like run out, or yeah, something can go wrong. I don't know exactly, something like that. But when a router cannot forward a datagram, it sends out a destination unreachable message to the originator and then discards it. So you got different codes. So you got code 0, which is network is unreachable, possible hardware failure. Network code 1 is host unreachable, possible hardware failure. Code 2, protocol unreachable. Upper layer protocol data is destined for cannot be reached for delivery. 3 is port unreachable. 4 is fragmentation required for routing to but DF. Yeah, so request timed out. There's an example of one of them. You've got, packets lost. All of it was lost. It just discarded it. Bam. This one was good. It received everything. Yeah, so there we go. This one lost here too. As you can see there, so ping statistics. Yeah, cool. So the time exceeded, incorrect configuration can lead to packets traveling in endless loops, so routing cycles. The ICP-MP time exceeded message is issued when a packet is sent. Its TTL is decremented by 1 at each loop. If the TTL reaches 0, the packet is dropped. Yeah, so that's what I actually meant to mean, the time exceeded when I'm talking about TTL. The router that is dropped, the protocol of which the TTL reaches in 0, sends a time exceeded message to the originator. If the destination does not receive all fragmentation in a set time, it drops any received fragments and sends a time exceeded message back to the originator. Echo request reply. A host or router that receives an echo request message creates an echo reply message and returns it to the originator. So echo request and echo reply messages can be used to help diagnose some network problems. E.G. Communication status between two devices. Testing destination reachability and providing status is achieved by invoking a ping command. Creates a series of echo request and echo reply messages providing statistical information. ICP-MP applications ping and trace out utility. So these are utilities you can use to ping and test if a network's working, and ping two devices to see if they're communicating, and etc. And trace cert is just checking the sort of hops you take in the routes that you get to get there. So tracer shows the path on how the packet traverses to its destinations. It provides names for all the intermediate routers on the path. It determines the path by sending a series of packets with the TTL fields of 1, 2, 3, and 4, etc. It causes each intermediate router on the path to send a time exceeded message back to the originator. So you got the example, TTL equals 1. So the create a probe packet, yep, goes back to router 1, TTL 0, packet will be discarded, time exceeded. And it goes back to the originator, as you can see. Let's go this for number 2, packet exceeded, boom, back to the person. And number 3, you get the point. Number 4, actually number 4, hold on, let's go back to that one. So number 4, hop is 4 limit, boom, boom, and TTL's 1, and yeah, nothing happened. So ICP provides a way to report errors to the originator. ICP provides error information, delivering errors, ICP routing behavior, reachability. ICP reports on errors, but is up to the IP host that receives the incoming IP messages to act on them reportedly. So that was a big video, guys. It was a lot of topic to get through. I hope you learned the basics of the application protocols. There's a lot more. There's tons more, but like those are just the most common ones you typically see. In the next one, we're going to be covering network security, so stay tuned for that. And leave any comments below if you enjoyed this or want me to go over any more content, because I can do that. But nonetheless, guys, enjoy, and I'll see you in the next one.